All right, pulley problem number 4. We are given the mass of these two objects. I'm gonna call this guy up here M1. This guy's gonna be M2. We're given how high M2 starts above the ground, right? Yeah, right here. The 2 kilogram mass is 1.5 meters above the floor, right there. What else do we know? It starts at rest. V initial is 0 meter per second. And then we're given the velocity when M2 strikes the floor. V final is 1.8 meter per second. So A, does that sound like information pertaining to forces or information pertaining to kinematics? This information right here, this information right there, that's kinematics. So the way this problem goes, the first question, determine the acceleration of the system. You're not going to be able to solve for the acceleration with forces. Why not? There's a reason. What do we not know about this problem? It has to do with M1 up here. We do not know the coefficient of friction between the 4 kilogram mass and the table. The coefficient is a question mark. In fact, that's what we're solving for in number 2. Okay? If we did have the coefficient of friction between M1 and the table, then you could solve for the acceleration by using forces, right? But for this problem, we have to find the acceleration with a kinematic. So we're going to go like this. Vf squared equals V initial squared plus 2ax. We're told that V initial is 0, so let's see right here, starts from rest. V initial is 0, so A is going to be Vf squared over 2x, 1.8 meter per second over 2 times 1.5 meters. So we get the acceleration as 1.08 meter per second squared. Now, we're going to take that acceleration and use it in the summing of the forces, right? We now know what the acceleration is. All right, so now let's look at the forces. So, in fact, I'm going to clean this up. I need some room to solve this. So I'm going to get rid of that. You have the questions. I'm going to get rid of this, and I'm going to draw my own. All right, so here's the table. So M1 is up there. Here's the pulley. Here's M2. Now, let's start with sign conventions. Sign conventions first. You want the sign conventions for each object to agree. In other words, you want the direction of motion to be positive for both objects. So which way is M1 going to move? Or I should say, which way is M1 going to accelerate in this problem? M1's going to accelerate to the right. So let's say to the right is plus, to the left is minus. That's for M1. And then up is plus, down is minus. This is our sign convention for M1. Now look, here's what happens. This sign convention is going to go around the pulley. So I'm going to go like this. So the motion goes like this. It hits the pulley. What happens? You rotate like that. You guys get what I'm saying? The motion goes around the pulley. So what are we going to be saying for M2? Down is plus. You know, basically the motion wraps the pulley, so the sign convention wraps the pulley. All right, so what are we going to be saying for M2? For M2, down is plus, up is minus. You should get in the habit of putting your sign convention right next to the diagram. It's not just for you, it's for the person grading your test. You know, on the AP exam, the free response, so they look at your test like, oh, that way's plus, got it. It just makes it easier, okay? All right, so let's put the forces in now. What forces are acting on M1? Well, gravity, we got M1G. M1 is on a surface, so we got a normal force. The rope is pulling to the right. That's tension. And then we're told that there's friction. Kinetic friction. Friction kinetic equals mu kinetic times normal force. Friction has an equation. Coefficient times normal force. All right, M2. What are the forces on M2? We have gravity pulling it down. That's M2G. And then we have tension pulling it up. Now, look. Which way is M2 going to accelerate? M2 is accelerating which way? Down. Why is M2... You guys got to stop. Why is M2 accelerating down? Because why? M2G is slightly bigger than T, right? If M2G is a little bit bigger than tension, which way is the net force? The net force is down. Net force and acceleration are always together. They're always together, net force and acceleration. Now, what if, just another question for you, what if tension and M2G were perfectly equal? If they were perfectly equal, what would the net force be for M2? 0, and then what would the acceleration be? 0, because F net equals ma. Get it? If your F net is 0, then your A is 0. Right? So what would be happening here? One of two things. If these two forces were equal to each other, one of two things. M2 would be either... Who can give me one? If these forces were equal, guys, it's not that hard of a question. If this force and this force were equal to each other, M2 would be either at rest or moving with a constant speed. It'd be moving at a constant speed. But just realize that's really kind of saying the same thing, because at rest is a type of constant speed. If you're at rest, you're constantly with a speed of 0. Okay? All right, let's keep going. Oh, I'm out of... It only lets me erase like 20 times. All right, so the free body diagrams are done. Now we go to summing of forces. So we're going to sum the forces for M1. We're going to sum the forces for M2. So focusing on M1, we sum forces X, we sum forces Y. Looking at M1, what are the forces in the X direction? In the X direction, we got tension to the right minus friction to the left. So I'm going to put in mu times normal force, because that's the equation for friction. Okay? Any other forces in the X direction? Nope. So this is equal to M1 acceleration in the X. M1A. Sum of the forces always equals MA. All right, now let's go to the Y direction. Looking in the Y direction, what are the forces? We have normal force up, M1G down. Any other forces in the vertical? No. So what is this going to equal? M1 acceleration in the Y. The sum of the forces always equals MA. Always, always, always. Now sometimes you can cross the A to 0. Is M1 accelerating in the vertical? No. So what can we do to this acceleration? We can cross this acceleration to what? 0. So this whole thing gets set equal to 0. But just be aware, technically it's equal to MA. We just set the A to 0. All right, now let's go to M2. Focusing on M2 and remembering that down is plus. Why is down plus? Because the motion is down. We're saying the direction of motion is positive. So we get M2G minus t, because remember, which way does t point? T points up, and up is negative. Okay. Sum of the forces equals ma. Guys, the hard part is officially done. When you get to this point, the rest of it is pretty reasonable algebra. I think you would agree. It's not crazy, crazy algebra. Okay, so what I would do, take this equation. What's the only thing in this equation that we don't have? T. Just plug the numbers in. You plug in for T, solve this equation for tension, you're going to get 17.44 newtons. One comment, see G right here? Are you going to plug in 9.8 or negative 9.8? 9.8. Don't plug in negative. Do you want to know why you don't plug in negative? Because you've already done the sign conventions. Look at what we did here. Did we or did we not pay attention to sign conventions? We did. So don't start throwing in more negatives after we've already handled all the sign conventions. You know what I'm saying? So just plug in 9.8. You get tension equal to 17.44. Take this equation. What can we get from this equation? From this equation here, we can solve for what? The normal force. We're going to need it in a second. We're going to need the normal force. When you solve for normal force, you get 39.2. Okay? And then finding the coefficient of friction. The second question is, what's the coefficient of friction? So take this equation, solve it for coefficient of kinetic friction. So the algebra is going to give T minus M1A over normal force. And you have everything. So tension is 17.44. M1 is 4 kilograms. The A, we already figured that out. Meter per second squared. The normal force is 39.2. So we end up getting a coefficient equal to, we'll round this to 0.34. The coefficient has no unit.